Hello students, so in today's lesson, we're going to take a look at chapter 3, Gravitation. Have you ever wondered, why do durians fall directly to the ground? Or have you ever looked at the sky and starts questioning yourself, why does the moon revolve around the earth? Well, all this happened because of gravitational force. Gravitational force is known as universe force because it acts between any two bodies in the universe. For example, you can see that between the sun and the earth exists gravitational force. Between the earth and the moon also exists gravitational force. In fact, even between the sun and the moon also exists gravitational force between them. This difference in sizes and also distance will affect the gravitational forces between them. So what's the relationship between all this? Let's see on the next slide. In the year 1687, Isaac Newton presented two relationships that involve gravitational force between two bodies. Okay, so the first one is gravitational force is directly proportional to the product of the masses of the two bodies. That is, F is directly proportional to m1 times m2. And also, he said that gravitational force is inversely proportional to the square of the distance between the centers of the two bodies. That is, F is inversely proportional to r squared. So this gravitational force exists between two bodies, and both bodies experience the same magnitude of force. Okay, from this two relationship, when we combine it, we got F is directly proportional to m1 times m2 over r squared. So now that we know gravitational force has the same magnitude between two bodies, why does a fallen leaf move towards the ground? Okay, because both the leaf and the earth experience the same gravitational force. This caused the leaf and the earth to move towards one another. And we know that since the earth is heavier than the leaf, that's why we can only notice that the leaf is moving towards the earth rather than the earth moving towards the leaf. And from the formula, we obtain F is equals to G times m1 times m2 divided by r squared. And we already know that m1 is mass for the first body, m2 is the mass for the second body, and r squared is the distance between the center of these two bodies. What about G? What is G here? So G is the gravitational constant that is already been obtained. You don't have to know how do we got the value for G. So you just need to use this value at the right time, at the right place. Let's see the example next. So the question asks to calculate the gravitational force between a durian and the earth. So here we have the mass of durian. We have the mass of the earth. Let's say mass of durian is m1 and mass of the earth is m2. And we also have distance between the center of the durian and the center of the earth. This is r. So just substitute into the formula, like in the solution here. Here we got m1 as we stated before, m2, r, and g. So from the formula for gravitational force, you just simply substitute everything into this, and you got the final answer. This is the force between these two bodies. Let's see next example. So a rocket at a launching pad experiences a gravitational force of 4.98. What is the mass of the rocket? So in this time, it asks us to find the second mass. So we can say that mass of the Earth here is m1, and distance already stated here r. You need to find m2. So if you want to try this first, you can pause the video, but if you already did this, you can check the solution here. Okay, so you already know the gravitational force, you already know the mass of the Earth, and what you're trying to find here is the mass of the rocket. So back to the original formula here, you substitute everything in here except m2 because you're trying to find m2. So after you substitute, you can rearrange to calculate the value for m2. Alright, next, let's see what are the effects of mass and distance between two objects on gravitational force. So these are the effects. When the mass is smaller, the gravitational force will also become smaller, but when the mass is become larger, the force also become larger. That's why you can see that force F1 is less than F2 because the bodies in F1 has smaller mass compared to bodies in F2. And next is the distance between the two bodies. The closer the two bodies, the stronger the force. That is why you can see here that F1 is greater than F2 because you can see F1 is closer compared to F2. Okay, let's look at this info file here. Even though gravitational force is a universal force, two persons on Earth will not feel the effect of the gravitational force. Why? Because the force between two bodies of small mass has a very small magnitude. That is why if you stand beside your friend, you won't really feel, actually you won't even feel there's a little bit of gravitational force between you two. Alright. Okay, since we already know the formula for gravitational force, now we're trying to relate the gravitational acceleration on the surface of the Earth with universal gravitational constant. So if you recall, according to Newton's second law of motion, the gravitational force can be expressed as F equals to mg. How come? We know that the original formula is F equals to ma, but when it is involving gravitational acceleration, we simply replace the a here with g, since a and g is acceleration. So does it make any difference when an object is on the surface of the Earth or when it is floating somewhere in the orbit? Let's see on the next slide. Okay, if you can see here, the picture here, it shows that the satellite is floating, it's not staying on the surface of the Earth. So you can see that the distance between the satellite and the center of the Earth is small r, and this small r consists of the radius of the Earth and also the height of the satellite from the surface of the Earth. That is why when we want to relate gravitational acceleration with a satellite from a distance from the surface of the Earth, we use r equals to capital R plus h, because it is the total distance between the satellite and the center of the Earth. And with this, the gravitational acceleration is written like this, where the R is a combination of R plus h. Meanwhile, when an object is on the surface of the Earth, we know that height is equals to 0, because if object is here, it means height is 0. Therefore, R is simply the radius of the Earth, and we can rewrite the equation like this, where m, the capital M, is the mass of the Earth. Okay, let's see an example. Mass of the Earth and the radius of the Earth. Calculate the gravitational acceleration on the surface of the Earth. So we know that on the surface of the Earth, it means h is equals to 0. So what do we do next? We simply list out the information you got from the question first. We have m here, we have r, and we have gravitational constant. We need to find acceleration. So the solution is on the next slide. If you want to try, you can try first and pause the video. If you already did this, you can resume and continue watching the next slide. So basically, this is what we did just now. You list out all the information you got from the question and then substitute everything into the formula and calculate this, and you got the final answer. Okay, let's see next question. A radar imaging satellite orbits around the Earth at a height of 480 km. Now we have h. H is this, but make sure this is in kilometer. You need to convert this into SI unit, so you need to turn kilometer into meter. So the question asks, what is the value of gravitational acceleration at the position of the satellite? You know g, you know mass, you know radius. Now simply use the formula, since it is orbiting the Earth. It's not at the surface of the Earth. Remember that R is equals to sum of capital R and also height. Okay, if you want to do this, you can do this first and pause the video. If you already did this, you can resume the video and continue watching the next slide. So this is the formula here. Basically everything is listed out. Just substitute into the formula and you will get your final answer. Make sure the unit is always written. Alright, now we're going to look at centripetal force. Centripetal force in the motion of satellites and planets. What are centripetal forces? So you can see that anything that is revolving around something, it has a circular motion. So the circular motion will cause the object to have a velocity that is 90 degrees from the centripetal force. So the centripetal force is always towards the center of the circular object. Okay, you have here that the satellite is revolving around the Earth in a circular motion, and the radius of the revolution is what we call as centripetal force, and if you see here that it makes a 90-degree angle, this is actually a tangent. This tangent is the direction of the velocity of the satellites. Okay, I have a video I want to show you. Let's watch together. So if you can see here that it is revolving this, what do you call this colorful thingy, it's revolving around the center of the object here. You can see that this is the center, and between this firework and the center there is a centripetal force, and this thing here, it shows that the direction of the velocity of the object here. You can see that it is making a straight line, right? So let's see, to get more understanding, let's see next video. Okay, you can see that the ball is rotating around the center, and we have the centripetal force. Centripetal force is always moving towards the center of the orbit, and this is the direction of the velocity. It's straight line, you can see. If you remove the force, then the velocity will actually show that it is moving in a straight line. Here too, an object is held by a string, and once we swing the object like this, you can see that it is rotating around this center. This rotation, it has a centripetal force towards the center. And yeah, that's it for this video. So let's see now. When we rotate the object, so this is the direction of the velocity of the object, and towards the center of the circle here, since we are using thread, we have a tension here, and this tension is what we call the centripetal force. Okay, so from this we have a formula to calculate the centripetal force by using velocity. We have mass of the object, we have linear speed or the velocity, and we also have the radius of the circle here. Now let's see an example. Figure 3.17 shows a hammer throw athlete swinging an iron ball in a horizontal circle before releasing it. What is the centripetal force that acts on the iron ball when the iron ball is moving at speed? So we have linear speed, we have radius here, and we also have mass. Back to the formula, force is equals to mv squared over r. So you just substitute m, substitute v, and substitute r here, and simply press your calculator and get your final answer. Now that we have velocity and centripetal force, we also have centripetal acceleration. What is centripetal acceleration? It is basically the acceleration that we calculate on a rotating object. Okay, if you look closely here, if you are throwing or you are launching an object with a low linear speed, the object will most likely fall and follow this trajectory. At one point it reaches the earth. But if the object is launched with sufficiently high linear speed, it will follow the second trajectory, which it will enter the certain orbit, and it will continue rotating around the earth in the orbit as a free falling object forever. it will not return to the Earth. So this object actually doesn't require any engine or thrust, because once any object is launched with a sufficiently high linear speed, it will follow the trajectory and circulate the Earth just like the Moon. So to calculate the centripetal acceleration, we compare the formula for force, whereby F is equals to ma, and the centripetal force F equals to mv squared over r. Since both have F here, we equate ma equals to mv squared over r, and on the left and the right side we have same m, we cross out m, that is why we got a is equals to v squared over r. Let's see an example now. Okay, figure 3.19 shows a weather satellite orbiting the Earth at a height h. Linear speed of the satellite is, the radius of the Earth r is given by, and what is the centripetal acceleration of this satellite? So you have height, you have what else? You have linear speed here, you have radius, and what else? So this is already sufficient to calculate the centripetal acceleration. If you want to try first, you can pause the video. If you already finished, you can continue. So the solution is, first you have to make sure you convert the height into SI unit, and just substitute everything into the formula. V squared over r plus h, because it is orbiting the Earth, that means it has height, it's not on the surface of the Earth. H is not equals to 0, so that is why you just substitute everything in here. So, and you got your final answer. Alright, now mass of the Earth and the Sun. So you can actually calculate the mass of the Earth and the Sun by using this formula, where m is the mass, r is the radius of the Moon or the object, g is the gravitational constant, and t is the period of revolution of the Moon around the Earth or the planet around the Sun. So in order to calculate, when you want to calculate the mass of the Earth, the radius is the radius of the satellite or the Moon, because the only thing that is orbiting the Earth is either the Moon or satellites. And t is the period of revolution, whereby if you want to calculate the mass of the Sun, you have to find it's basically the same thing, except that r is radius of the orbit of any planet. Any planet will do, and t is the period of revolution of the planet. Let's say if you want to use Mars, then r is the radius of Mars from the Sun, and t is the period of revolution of Mars from the Sun. Now let's see example. Figure 3.23 shows Mercury orbiting the Sun with a radius. We have a radius here, and the period of revolution, we have period in seconds. Calculate the mass of the Sun. We have r also here. If you want to try this first, you can pause the video, but if you already did this, you can resume and check the answer. So we use the same formula as shown previously. Use the formula to calculate the mass of the sun. So you have the radius of orbital r here. You also have period of revolution here, and you have g. G is the same g lah. So you substitute everything into the formula and you get the final answer. This is the mass of the Earth. This is the mass of the Sun. It will be the same if, let's say, the question changed Mercury to other planet. The answer should be the same because the radius will change and the period also will change. So this change will be consistent, that the value of m will be fixed if you calculate it correctly. So this is the end of my online class. So after you finish watching this video, please complete the gravitation module for 3.1 and answer in your notebook the formative practice 3.1 on page 95 from the textbook. If you have any question, you can ask me directly or in your class group. Either one is okay. Just make sure you do, and please submit your attendance before the end of our class. That will be it. Thank you.